Okay, so I'm going to be going over the acid catalyzed dehydration. I'm going to be going over quiz 5 today. This was over chapter 7, and I'm going to start with question 1. The following reaction undergoes acid catalyzed dehydration by an E1 mechanism, so I know the mechanisms for that. In boxes provided, draw out the mechanism for each step of the reaction, the intermediate products, and the final product. Be sure to consider rearrangement of the intermediates and draw the rearranged intermediate where appropriate. Okay, so I just know to start, this is going to attack the H2SO4. So a lot of times, to make it easier to draw the arrows, I redraw H2SO4 like HHSO4. This is going to attack and the bond is going to break. Oh, I should probably do it down here in this box, actually. So OH with HSO4 and heat. So heat helps me know it would be an elimination reaction if they hadn't already told me, but that's going to leave us with OH2 plus and HSO4 minus. So that's the first step. The second step is the leaving group is going to leave. So I'll redraw this here. Leaving group leaves and we get a carbocation, but that will rearrange. A hydrogen here will shift over, and your carbocation will be there. Okay, and then, so that's step 2 arrows and the intermediate, which rearranges, and then step 3 arrows in the final product. So this is an elimination reaction, so the water or the HSO4 minus in the solution will come and abstract this proton, and that will fill in where the carbocation was, and this should be your final product. Oh, I didn't have it on the screen that whole time. So the HSO4 takes this proton, it leaves the electrons behind, which form a double bond to fill in this carbocation, and you get your final product. Anytime you see a carbocation, a little flag should go off that says, wait, look for rearrangement, look for rearrangement. I always try to remember that. Okay, with the following E2 reaction, generate E or Z. So the first step on this is to draw the Newman projection. So I'm going to draw it as if I'm looking right here from carbon 1, 2, 3 to 4, because that's where the elimination will happen. So carbon 3, the bromine, if I'm looking at it, like say it's coming out towards us, and this hydrogen is going into the page, and I'm looking at it from this angle. So from this angle, the bromine would be on the right, and the hydrogen will be on the left, and then in the plane of the page goes straight down. And then in the back, the CH3 is also coming out at us, so it'd be on that side, and the hydrogen's going into the page, so it'd be on the left. So if it was going into the page, say this is the plane of the page, this is going into the page, so if I turn, it's on the left. And then here we go. Okay, so then I know H and Br have to be anticoplanar. That helps us determine if it's E or Z. So these are going to get eliminated, and that's what forms the double bond. So then the H and the ethyl group will be on the same side, and the isopropyl and the methyl would be on the when I say on the same side, they would both be on top of the double bond or on bottom of the double bond, and then H and isopropyl are both on the left, and the ethyl and the methyl are both on the right. So then we identify priority. Carbon is a higher molecular weight than hydrogen, so this is a higher priority group. These are both carbons, but this carbon is attached to another carbon and 2 hydrogens, and this carbon is only attached to 3 hydrogens, so this carbon is higher priority. So these are on the opposite side, so this would be an E product. Okay, in the box provided, draw the most likely product of the following reaction. Okay, so this has a good leaving group, and it has a negative nucleophile, so this is probably going to be a strong nucleophile, so this is going to favor the 2 side. But it's also big and bulky, and this is secondary, so I think it's going to be E2 rather than SN2. And because it's big and bulky, it's also going to favor the Hoffman. So that means it's going to not form the more stable alkene. It's going to form actually the less stable alkene. because that hydrogen is easier to get to than trying to get in here to get this hydrogen on this side. So it's going to come take this. The electrons will get left behind and form a double bond as this leaving group leaves. And you'll end up with your alkene. Predict structures A and B. Please box your answer. So this is actually really similar to what we did in recitation at the very end. If you have a hydrogen with NH2 minus, it's going to, on an alkyne, it'll deprotonate that and make that alkyne be a carbanion. So that's intermediate A. And then intermediate A will attack this bromine and do an SN2 reaction. And that would be your final product. So this is a good example of a multi-step synthesis. And these carbons, 1, 2, 3, 4, I usually will count them just to make sure I didn't lose them. And then you start with 1, 2, and then that. Okay, and if you wanted to turn this into an alkene, you could do a poison catalyst to do so, either cis or trans, whichever you wanted to do. For the bonus question, consider how the reaction given in question 3 above, consider this above. If sodium methoxide was used as the nucleophile, how would that change the most likely product? So it would give the zaitsev product instead. And you could have explained this with words or drawn it, but it would make the more stable one because it's more narrow. So it's not going to give you the Hoffman product. Okay, I hope that was helpful for you guys. Please reach out if you have any questions for me.